Hey, welcome back. This lecture is going to be continuing where we left off last time with AVL trees. By the end of this lecture, you will understand how to do AVL trees, or I mean, you'll have been given the utilities by which you can understand how to do AVL trees, and then that'll tie in with the section as we start as Adam's section lecture discusses some more examples and such. The idea then will be in the third AVL tree lecture. I'm going to go over kind of viewing things from a different route, just to give you a more conceptual understanding of why things work the way they do. So here we're just sort of learning the algorithm some more, and then on the lecture after this, what we will be doing is instead of learning the algorithm, we'll know it already, and it'll be more of a conceptual take on why the algorithm works the way it does. So where we left off last time, we had discussed the single rotation. The idea behind the single rotation was we went from this setup here we had a subtree A that was height h. We had inserted a value into it and made it instead h plus 1. And then the subtree B was here, and that was height h. And a subtree C was here, and that was height h. That was h plus 1 turned h plus 2. That was h plus 2 turned h plus 3 with the insertion. The balance here went to -1. The balance there went to -2. That was our setup with the changes. The scratched out parts are what changed as a result of that insertion into A, and are what used to be, and then the parts written above that are the changes as a result. So K1 was height h plus 1, balance 0. Now it's height h plus 2, balance -1. And then we said, looking at the single rotation code, what that ended up being was we had this transition here, where we said here we had height A, which was overall h plus 1. We had here B and C, which were overall h each, making that h plus 1, balance 0, height h plus 2. So we did that last time. That's how we had done things. And if this is, say, a pointer PTR, which is a reference to either the right or left pointer of the parent of K2 originally. There's some parent node that points to this. Either that or the root pointer itself, if this happens to be the root. And the idea is, given that pointer, how do we make this code work? And we can look at this and say, well, we're making some pretty large-scale rearrangement of the tree. I mean, B could be a very large tree here, and it's moved over to the other side. That's a pretty big deal. However, notice if you can ignore for the fact that it's a tree and just view this as sort of pictures we're moving around here, 2 circles and 3 triangles, we haven't really made that complex of a movement in terms of where the attachments are. So there's a lot of nodes being moved around, but the beauty of linked memory is that you can move a huge collection of nodes from one spot to the other just by changing the pointer to the top node. By changing the fact, instead of having K1's right pointer point to B, I have K2's left pointer point to B. Now a whole bunch of nodes have moved over to K2 with this change of one pointer value. So potentially this is really straightforward to do. And in fact, we can get it done very quickly. What's going to happen here is we will have, let me draw the picture again. I'm not going to bother drawing the heights and such now. We're just going to concern ourselves with the structure for the moment. So here's height. Here's subtree A and B and C. And here's PTR. And the first thing we want is we're going to want to eventually change this to point to B. And we can't change that pointer without saving K1's address, because right now this pointer is the only one that holds K1's address. So let's start out by saying we need some sort of tree node pointer temp equals pointer arrow left. So that, in other words, what we'll have here is some temp. Once we've done that, now we say, great, now I can change K2's left pointer. Or in other words, I can change pointer arrow left because I've saved the value of pointer arrow left. Now I can change it because it's saved somewhere else safely. And what do we want to change it to? Well, we want it to point to B, and that means that that's going to be temp right. Pointer left equals temp right. Actually, just to make sure I don't run off the end of the viewing, let me write it down here. It's the same code I just wrote. I just want to make sure it all shows up on your video slide. So that's probably the better way to put it. So in other words, here we're saying this should no longer point to here. This should now point down to here instead. So now K2 is pointing to B. And since I've saved temp right, I can now free this pointer. It used to be that the root of the subtree B was only held by this pointer. I couldn't change it. Now I've saved the root of subtree B in a different place. I can now change temp right as well. I can change this pointer. And where I want it to point is to point up to K2. And this is getting very complicated. I'm going to redraw it in a moment. So we have K1 point up there. K1's right, rather. And then the last thing to do is say, well, now this original thing should point down to K1. Pointer equals temp. In other words, if I sort of pull this over and attempt to kind of draw this in here, what we're dealing with here is something that looks like this, where I have here, I'm going to space this out a bit more, K2, K1, A, B, and C. And they end up saying, well, first I'll have a temp pointing to here. Then this gets changed to point down here, which is what we want. We want K2 to be pointing to B and C. Then, let me perhaps bump this up a bit, then this gets changed to point over to here, which is what we also want. We want K1 to be pointing to A and K2. And then finally, whatever used to point to here now gets changed to point down to here instead. And it's still a little hard to see, but if you sort of follow the path here, it's a bit easier to see than the earlier diagram. What used to point to the root now points to K1. K1 points to A and K2. K2 points to B and C. And that's exactly what we wanted in our diagram. If we put the original diagram back, perhaps I can even tuck it in here a bit. Hopefully this all shows up on your, I can see it all, but I'm not sure if you can see it all on your video slide if there's edges cut off. But this is the basic idea here. We used to have K1 pointing to A and B. We used to have K2 pointing to K1, but we changed K2's left pointer to point to B when we said pointer left equals temp right. Then we said temp right shouldn't point to B anymore. It should point up to what the root pointer pointed to, which was K2. And then we changed the root pointer to point down to K1 where temp pointed. And so now we can sort of see the same thing we got here. K1 pointing to A and K2, A and K2. K2 points to B and C. K2 points to B and C. So it all works out okay. So hopefully if you draw that out yourself a few times and run through this code, it might be clearer because you can kind of space things out as much as you need to make it clear. But hopefully that clears it up a little bit as far as the nodes are arranged in this picture the way they would be originally, and all we've done here is now we've connected them the way they should be connected here, but arranged them the way where they were arranged in their original picture. So, and that maybe is a little clearer how things are being modified. The point being that we only needed 4 assignments to do this. We saved the left node, so therefore we could change the pointer to the left node to point to B. So therefore we could change the old pointer to B to point to the old root, and therefore we can change the pointer to the old root to point to what we saved. And so it's sort of a big colossal swap where in every step what we save is then being written to. We save temp right and write to it. We save pointer and then write to it. And when we're all done, then temp goes away and we've achieved what we want. So it should be clear that that result of that operation then is constant time. There's only 4 pointer assignments, and so as a result, that's constant. The other thing to mention is that this is a single right. Single left is the mirror image. What's going to happen with the single left rotation is exactly the opposite. We're going to move K2 up and K1 to be the left child of that, so sort of a twist. A and C stay where they are, and B moves over to become the left child of K1. Or in other words, if we look back at the code but simply swap the words right and left, we'd be saying that we have here, and I'm going to go ahead and draw a single left rotation here. If I have here K1, K2, here's B, here's C, and here's A, again, more spaced out. If I said temp equals pointer right, then said pointer right equals temp left, remember this is pointer up here, then said temp left, temp left here equals pointer, then I'm saying that this should be pointing to here, and then pointer is temp, I would move pointer to here. And you can see then we have here pointer, the root is K2, which points to K1 and C, which K1 points to A and B, and that was our original picture. So the idea here being that the code would work for single left rotation if you just swap around the words right and left. Whenever I say left in this code, you say right, and whenever I said right in this code, you say left, and there's a code for the single left rotation. The reason being that the two are exact opposites. Now, of course, only one of them is going to work at any one point. When I've got a mistake here, if I do the single right to fix it, if I take that fixed tree and do a single left, it's going to make it bad again. So I'm talking about structurally, the two are inverse operations. If I take a tree and do a single right and then a single left, I'm exactly back where I started. And so if you understand how we went from here to here for the single right, the single left you should understand as well. It's just the reverse image. And certainly if we had a problem situation like this, but reversed, then a single left would fix that. In the same way a single right fixed this problem. So that's the first two rotations. The single right, which we've looked at an example of, and the single left, which is the reverse. What we're going to do now is look at the double rotation, which is a little interesting in and of itself. And the motivation for the double rotation, you're probably going to want to sketch this down in notes at some point because I will not be able to fit all the different iterations of our repair work on one slide. I'm going to have to kind of do it slide by slide, unfortunately. We have here the pointer to K2. In other words, we'll start out exactly the same way. K1, A has height H, subtree B has height H, and then subtree C has height H. This is H plus 1 with balance 0, balance minus 1, H plus 2, blah, 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 blah. So that's the same situation we started at with the single rotation. And we're going to basically do an insert again. So far, again, exactly like the single rotation example. However, this time we're going to insert into B. Rules will apply as before. We will say however I'm inserting into B here, we're going to say B remains legal. So we're not going to worry about what's happening in B. We'll assume that everything's still okay as far as this insertion went. It just happens to be an insertion that increases the height of subtree B. It kind of breaks below that bottom part and says, well, now this is one level deeper than everything else. That increases the height of B to H plus 1, but we'll assume the subtree B with this node added in is still a legal AVL tree. We're not going to worry about those details, or at least not quite yet. The details we're concerned about is how everything's affected here, and the effect is as before. This increases to H plus 2, the balance changes, this time to plus 1 instead of minus 1, because it's the right subtree that increased in height and not the left. So now B is 1 more than A instead of being 1 less than A in height. And then up here, the height here increases to H plus 3, and we have here a minus 2. So the situation is exactly the same as for the single rotation, except for two things. Firstly, this balance is plus 1 instead of minus 1. And secondly, it's B that has the increased height, not A. Other than that, it is exactly the same layout. So let's go ahead and do a single rotation, single right rotation as before, and try and fix this. And if we do something like that, and like I said, I'm going to need to have you have this sketched out in front of you because I need to replace it. K1 and K2 will go like that. C remains, A remains, and B moves over. Just as with the single, the whole height here, actually, I'm going to write the height up here. The whole height of B is h plus 1 with the addition of the new node. So we haven't changed any heights, we've just changed the structural arrangement of the tree, just like the single rotation, exactly the same as before. And so you ask, well, then why am I making such a big deal about this? The reason is, now take a look at the balances and heights. The height here is still h plus 2, because the maximum of the two subtrees is h plus 1, and then you add 1 to that. The balance is h minus quantity h plus 1, which is going to be minus 1, as you expect because the left subtree is greater than the right. And then the height here is h plus 2, the height of A is h. That means the balance here is plus 2, and then of course the height is h plus 3. That is, all the single rotation has managed to do in this case is we've moved the problem over to the other side. We still have an imbalance, but in the previous slide, if I can put that up for a moment again, in the previous slide, the balance problem was on the left-hand side of the overall tree, and we had therefore had a balance of minus 2 because the left side was 2 greater than the right. And when we've done this single rotation, we moved k up to the root, k2 down to the right child, A stays the left child of k1, C remains the right child of k2, and B breaks off to attach to k2 instead. But since B was the subtree that was causing the problem, B was the subtree with the greater level of nodes, or greater height. As a result, moving B from one side to the other is not going to fix the problem. It was different when we had A. If A was the tree that was greater height, well, we've sort of raised it a level by saying, well, you don't just go up to K1 to reach the parent of the subtree. You go up one further level to K2. That was in the previous diagram. Now we just go up to K1 and we're at the root. So in a sense, the sort of overall depth of A's deepest nodes has dropped a level, and when A was causing the problem, that was exactly what we wanted. But here in B, nothing's changed for B. The nodes are still as deep as they ever were, and so we still have a problem. One other way to think about this is to sort of view it as weights. And again, my art is bad. I'm trying to draw a pan with two balances, where as you put on weights, they balance out. It never looks anything like that, but bear with me. Say we have a balanced pan here, where I say I've got a very large weight called A and a very small weight called B. And then up here I have a small weight called C. When we do that, we say, well, if I'm trying to balance this balance bar, I can say, you know, take this little weight B and move it over, and that seems like it would balance things out. I'll then have a very heavy weight A on this side, and on this side, I'd have two small weights, B and C, and they would balance each other out. That was the single right rotation. We said I had a subtree A that had greater height. B and C were the original smaller height of H. And so if I took B off the pan and moved it over to the other side, well, then I'd have B and C, two small weights on one side and the heavier weight on the other, and that was in effect a single right rotation. That's what we are trying to do here. And in the original idea we looked at yesterday, that worked. But we basically moved B from one side to the other. So that's why this is a nice analogy. For the single rotation, it works, because A is the heavier tree. However, the situation we're arriving at now is I have this situation. Where A is the smaller weight, and B is the heavier weight. And C is, again, a small weight. If I move B over to the other side, I just end up with a situation like this, where I have small weight A and a heavy weight B and a small weight C. And that's kind of the problem we're getting if you want a real-world analogy to sort of tie your mind to with regards to the AVL tree picture you looked at in the last slide. This is our double rotation, the issue that's going to lead to a double rotation. This is the problem we ran into. When we inserted it into B, B became the heavier subtree, or in a sense the heavier weight. Taking B and moving it over to the other side doesn't do us any good. We just now have A and C are of equal size, and we just move B over and we tip the pan the other way. And that's the problem here. That's why this doesn't work, because the whole point of this rotation is to sort of, move a few nodes over to the other side to balance things out. But here we're taking the whole large clump and moving it to the other side, so now we just have a large weight on the other side. It's the exact same problem. And it seems, I'm going to sort of scroll this upwards. It seems that if this is our goal to repair the problem, one way to do this might be to say, well, instead, let me take that and do this instead. I can balance this out by having B on this side A and C here. Large B on one side, A and C on the other. After all, that's what we did up here, right? Or, I'm sorry, scroll down. The quote-unquote single rotation version, that's what we did. We had the large tree on one side and the smaller weights on the other side. And so there's an argument to be made that, hey, we can do the same thing here and have the large weight on one side, the small weights on the other side. And so what we'll do is, and we'll as we did before, we'll take the smaller weight and move the smaller weight over to the right side, and that should balance things out. However, we cannot do this. And I'm going to let you pause for a moment and think about why that is, unless you see it already. Then, of course, you don't have to hit pause. But I'm sort of going to leave you a moment to think about the question, why won't this be a viable solution? Okay? And the reason it's not a viable solution is it works just fine with weights in the real world. But we have an additional constraint that we didn't have on if this was actually a balanced pan with weights, which is that this is supposed to be a binary search tree. So when I say I've got this situation, remember I need to be able to say, in order to find B, B is going to be, as it was before the rotation, greater than K1, less than K2. If I keep B on this side, on the left side of K1, we're then implying it's less than K1, and the original tree, that was not the case. B was in the original tree greater than K1. We have to keep it to the right of K1, and we have to keep it to the left of K2. And so this rotation structurally does that. The heights are off. But in terms of structural relations, this works. B stays in terms of a binary search tree operation what it's supposed to be. And that's what we're missing from this weight idea, is there's no restriction in the real world with weights on the order of things, but in reality we don't have that same flexibility. We have to keep B to the, and if we're going to have this actually be an accurate model, B has to stay to the right of A, C has to stay to the right of B because of the way the nodes compare to each other in terms of order. Everything in B is larger than A, everything in C is larger than everything in B. So this is not going to work. Whoops. Good. So what do? We've got this situation. I can't just move B over because that doesn't work, but I can't keep B on this side and move A over because that violates the ordering principle. We don't really have any other viable solution here, unless you happen to have a neighbor who's got nice power tools, a good hammer or a saw or something like that. Because through the use of power tools, we might say, let's have the ultimate fix here. We'll balance this pan out by simply taking a hammer to these weights and breaking B in half. And that's how we can fix this problem here. What we can say is, if I break B in half, I can keep the bottom half of B on the left pan and put the top half of B on the right pan. And now I've got a small weight and half of the large weight on each pan, and the pan should balance. I can't just move the large weight around. That doesn't work. I can't leave the large weight by itself because that violates our ordering principle. But I could break the large weight in half and put one half on each pan. That should fix the problem. So, if we keep that analogy in mind, the question now becomes, how do we take that analogy and apply it to our original tree? This was the original tree that had a problem. I have this analogy of breaking B in half. How do we do that? And the answer is, well, it's not a problem. The B here is a tree. It's a root with two subtrees. We just didn't look at that level of detail because we didn't care about it before. We said, I've inserted into it, but I don't care how. Let's take a look at one more level of detail. We won't look at the subtrees involved, but we will look at least one more level of detail. And let's remind ourselves that when we draw the subtree B, what's really going on here is this is some root, let's call it K3, with two subtrees, say B prime and B double prime. And so when we say this is height h, what's really going on is each of these is h minus 1, and so then that's height h with a balance of 0. One of them could have been h minus 2 as well, and the balance then would have been plus or minus 1. Again, as before, there are many different things. The specific example we'll look at, both of these will be height h minus 1, just like everything was h in the original example for the A, B, and C heights. Don't worry about what happens if they're different. Eventually you'll be able to deal with everything. We just have to pick some specific example, so I'll pick the one where both of these are of equal height. So that's really what's going on. And then this whole thing is B. Which means when I draw this picture and say I inserted into B and made this h plus 1, and that's the picture we've been drawing on the last slide, what's really going on is, if I look at one deeper level of detail, I had here B prime, which was of height h minus 1, and I had B double prime, which used to be of height h minus 1, but I inserted a node into there. And again, we'll say, I don't care where it got inserted into B prime. The point is, B prime remains legal, and we're just going to stick this node in. It happens to be one that increases the height of B prime. Just like I did for B originally, I'm saying, well, what's really going on here is it was inserted into this subtree. We didn't care where at all before. Now we're saying I at least know it's inserted into the right subtree. We don't care where inside the right subtree. All we know is that then this increases to height h, which this was really height h. That increases to h plus 1. That balance that was 0 originally now increases to plus 1. So if we kind of lift the lid off the B subtree and look at things, then that's how things are. We have here the idea of the, we have two subtrees of B, and we're inserting into one of them, and by having that subtree now be height h instead of h minus 1, the entire tree height increases to h plus 1, and that's what we saw overall here. This is just a little bit more detail about what's going on underneath this sort of cover that just says B on the cover. Now, what's going on in these two subtrees? We don't care. Just as we didn't care what was going on in here before, we say, well, now, unfortunately, we have to care about what's going on in here. We'll lift the lid and look inside, and this is what's going on. We don't need to lift those lids. This is as much detail as we need. We didn't even need this much detail for a single rotation. For a single rotation, all we needed was this. For a double rotation, which is what we're about to look at, we need to look at one deeper level of detail. Look at this in terms of a root and subtrees, and that's as deep as we need to go in terms of detail. Point being, however, I'm going to redraw this picture now, but instead of having the subtree B look like that, I'm going to redraw it. Instead of looking like that, it's going to look like that. Don't get confused by that. I'm not changing anything else in the original diagram. I'm simply drawing B with a little bit more detail than we had before. So everything else is going to be exactly the same. We will have here pointer K2, K1, A, which is of height h, and C, which is of height h. This will originally be h plus 1 with a balance of 0. That will originally be minus 1 with a height of h plus 2. And then B will be there. Everything else is exactly the same as it was before. Actually, let me do one more thing here. The height of what I'm going to draw will originally be h. The only difference is, instead of just drawing a triangle there, I'm instead going to draw the root and two subtrees represented by that triangle. So I have here B prime and B double prime. This is h minus 1. This is h minus 1. And then that we could put a balance there if we want, though it won't really matter to our looking at things. So we have that. And I want to stress again, nothing is different here. This is B. We drew it just as B before. Now we're looking at a little bit more detail, but it's essentially the same tree. And so when we do the insert, now we insert in one of these two subtrees. We picked this one before. We could have done B prime as well. We just happened to say, well, let's insert into B double prime in this example. That increases to h. That increases to h plus 1 with a balance of plus 1. So now we have the original picture of the entire tree B going from h to h plus 1, which is what we had in the previous picture. The entire tree B going from h to h plus 1 because of an insertion. That's what we see here. Exact same idea, just different level of detail. And so now that we're done with this, we then say, well, that changes this to h plus 2, makes it a balance of plus 1, and that makes this h plus 3 with a balance of minus 2. So exact same changes as before. Again, all that we have here is we're seeing a little bit more detail than we saw before. So given that, we can now start worrying about the double rotation operation. We've already seen a single rotation won't work. That was the whole discussion with the weights. So we're saying by looking at a little bit more detail of that subtree B, this now in effect enables us to break things in half. This is why we're doing this. Looking at the weights told us that the only way to balance the two pans in the balance were to break the large weight B in half and put half on one side and half on the other. And if we remind ourselves, by looking at this picture, that the subtree B is really composed of two subtrees of its own with a root, then in that case, what we know is that I could put B prime on one side and B double prime on the other, and that should balance things out. That is, in the same way that the weights could be balanced out by breaking B in half and putting half of B on each side, by breaking the overall subtree B in half, B prime being one half and B double prime being the other half, by putting those on different sides, one with A and one with C, that should balance things out, or at least it's worth a shot. And that's what we're going to do. We're going to eventually have A and B prime on one side as subtrees, B prime and C on the other side, which begs the question, what will be the root of the overall subtree? It can't be K2. Both of these are less than K2. So they can't be on different sides if K2 is the root. It also can't be K1. Both of these are greater than K1. So if K1 is the root, then both of those have to be on the right. However, K3 separates these. One of them is less than K3. One of them is greater than K3. And that tells us that if K3 was the root, this would work. If K3 was the root, A and K1 are less than K3, and so is B prime. Those could be to the left of K3. Likewise, because this is on the left of K2, K2 is greater than K3, and likewise C, therefore, is greater than K3. And likewise, B prime is greater than K3. So K3 were the root, B prime, K2, and C could be on the right side of K3. So we will create a tree that has K1, A, and B prime making up a left subtree, B prime, K2, and C making up a right subtree, and K3 being the root. Now if you can just jump to that result in your mind, you're all set. but most people can't, especially when they're first learning this. So the way I'm going to teach this is the double rotation's goal is to get K3 up to the root. And since a single rotation could move K3 up one level, and we have 2 levels to go, we need to do two single rotations. So you can think of a double rotation as being made of 2 single rotations. In reality, the double rotation, all it's doing here is it's saying K3, these form a tree, these form a tree, K3 is the root. And that's the double rotation. So like I said, if you can remember just to do that, that's okay. I would not advise it, though. I would say as you're learning this, learn it the way I'm about to teach it. It's probably going to be a lot easier for you. It's called a double rotation because it is in effect made up of 2 singles. The first one is going to be doing our twist here between K1 and K3. We will first do a single left on K1, moving K3 up to be the root of that subtree and K1 down to be the left child. That will position K3 right here so that when we eventually do step 2, which will be our single right, that will move K3 from this position to the root of the overall tree. In other words, we still end with the single right rotation. We already saw that the single right alone isn't going to work. But the single right, if it is preceded by a single left on the left child, that will work okay. So your double rotation here, double right rotation, is step 2 would be a single, or I should say double right on a node. Step 2 is going to be a single right on the node. Step 1 is going to be a preparatory step, which will consist of a single left on the left child. So the double right rotation on a node, say on K2, consists of you first have a preparatory step, do a single left rotation on the left child. That will move more nodes to this side. K3 moves up to become the root. A and B prime will be sitting on this side, on the outer edge. There'll be more nodes there and fewer nodes sitting in the middle. And then single right rotation on the node, which is what we wanted to do in the first place. Now that the heavier portion of nodes is on the outer end instead of the inner end, now more nodes will lose a level and fewer nodes will just jump down to the other side. So the idea is here, this preparatory step gets stuff on the outer edge so that the eventual single right rotation in K2 corrects things. And that's the idea. A double right rotation is used where single rights would not work, and yet you want to move to the right. And you'll still end with a single right. The issue is you're simply going to do a preparatory part of this so that the single right will work. And that preparatory step will be a rotation in and of itself, and so effectively you do 2 single rotations, and therefore it's called a double rotation operation. If you're going to count how many rotations are done, this still counts as 1 rotation. A double rotation is 1 rotation. It just happens to be composed of 2 singles. So that's an easy way to remember how to do it. So again, this is something that you'll have to have sketched in your notebook because I can't keep this slide up as I write the rest of the procedure. Step 1 is going to finish up, remember, not touching this part at all. We'll still have pointer to K2 to C. That part's not touched at all. Rotations are local operations. You have a pointer to the root of the subtree that the rotation's working on, and that doesn't change anything. That's why we never had to look at the parent. In all these diagrams, yes, there's a parent node up here. The parent doesn't care what's going on. We just have this tree itself. And then we do the rotation and fix this, and it has nothing to do with the parent or anything else later on in the tree. Likewise, as I start to run this rotation, these parts are not affected. All that matters is we have a pointer to K1, and now we start doing a rotation on K1, and that'll affect the subtree that that pointer points to, but won't affect any of K2 or C. So those can stay exactly the same. And that single left rotation will move K3 up to be here, move K1 down, and we'll have here, off of K1, the subtree A, which is of height h, and the subtree B prime, which is of height h minus 1, and we'll have the subtree B double prime, which with this insert is of height h on its own. Meaning here we have height h plus 1 with a balance of minus 1. Here we have height h plus 2 with a balance of minus 1, and then this still remains exactly what it was before. This is the part, this part didn't change. This is the part that has changed. Height of the root of that subtree, we have this pointer to all of it, and now this pointer, whatever it points to, used to be k1, now it's k3. The height is still h plus 2, and as you can see, the rest of it. If there's some illegal things, right now there isn't, if there happen to be some illegal things introduced here, it wouldn't be a problem, because we're not done yet. This is just step 1 of 2. It's okay for things to be messed up while we're manipulating the tree, as long as they're fixed once we're done. So step 1 is completed. We've done this rotation here and fixed that. Now we need to do step 2, which is to do a single right rotation on K2, and that will move K3 up to become the root, K2 down to become the right child. So we will have this. The right subtree of K2 was C. That's still okay. H. The left subtree of K3, in effect, quote unquote, the A subtree, is all of this here. That part is the large clump that was subtree, it was called A in the various examples we did. But now if you sort of try and apply that single rotation pattern, we had 3 subtrees that were called A, B, and C. The C is still C. This is where the B position is. This is where the A position is, that whole clump of stuff, which now we don't care about the detail involved anymore. But let's move that clump of stuff upwards as K3 moves upwards. And then finally, this is the B position of that earlier, single right rotation we looked at. If we're going to match these subtrees to the ones we had in that first example, this would be the quote-unquote B subtree, and that's the one that moves over to become the left child of K2. So we have here that, actually I should maybe draw this a little bit lower. This is B double prime. Used to be H minus 1. Now I'm trying to basically make these look even in height, so ignore those center lines now. Those don't even worry about those. This now is of height H, which it was even way back when here. So we had B double prime went to height H with the insertion, and that's what we've got here as well. Because of that insertion, it went to H. So that's the tree that moves over. And sorry about the sort of extra additions there. I was just trying to kind of line it up. A and C, and with the addition B prime, are all of height H. That's of height H minus 1. And now if you quickly figure out the remaining heights, H plus 1, balance 0, balance minus 1, H plus 1, balance 0, H plus 2. So things are fixed. That's all we needed to do. And that's the double rotation. So we did a left rotation on the left child, and then a right rotation like we wanted to do to begin with on the root, and that fixed this whole thing up. Now notice that whenever we dropped to level and height again, we had, after the insertion, things were H plus 3. This brought it back down to H plus 2. That's going to be important for us later on. In general, with one exception that we'll talk about in next lecture, the rotation on a imbalanced node will always drop the balance from plus or minus 2 to 0, and will drop the height down 1 level. And so, but we'll talk about that later on. Now, as far as picking out which rotation we want to do, or I'm sorry, what rotation we want to do here, we had said there were 3 things we need to worry about: where to apply the rotation, which rotation to apply, and then how to do it. You now have seen how to do all the rotations. You saw the single left, or single right rather. Single left was just a mirror image of that. Then you saw the double right just now. And the double left would just be a mirror image of that. For the double left, you do a right rotation on the right child and then a left rotation on the node itself. So that just kind of is a mirror image of this case. Where to apply the rotation? Well, that's at any node that is has a balance of plus or minus 2. And you're going to be returning from your binary search tree recursive calls, you'll check things on the way up. So as far as the answer to the where question, this is your tree. You'll do your insert or removal as you work your way down. And then as you return from your recursive calls, you'll have here, let's say, a node here, and a node here, and a node here, and a node here. As you return from your recursive calls, you're basically moving back up the tree one by one, checking those nodes. So that will be the order in which you'll be looking at things. You trace a path from root to leaf as you do an insert or removal for a binary search tree operation. Then as you return from your recursive calls, you're tracing a path back up to the root. And you will inspect your nodes in that order. Along the path you looked at, those will be the nodes you look at. And if at any point a node has a bad balance, you fix it. So you are, as you return, fixing the heights of these. AVL trees would only work efficiently if you stored the height inside the node itself. And what you'd be doing here then is saying, well, if I've made an addition here, if this height is 0 and I insert here, this height for the parent becomes 1, and the balance will change. And then I come up here, and maybe that height has changed as a result of its child changing. And I come up here, and maybe that height's changed as a result of that, and so on. So as we return from a child back up to its parent, we then, in that parent, check the heights of the subtrees, figure out our own new height, our own new balance, and at any point where the balance has become plus or minus 2, then that would be where you apply a rotation. So you could, in theory, be applying a rotation at every node back up to the root. That's at most log n rotations. One of the parent of where you just did something, and the parent of that, and the parent of that, and the parent of that, and so on up to where you started at the root. And we said each rotation was constant time. And kind of looking at the subtrees and calculating your own height from that is constant time. So we'll be doing a constant amount of work at each node, and as we have at most log n nodes, so therefore we know the amount of work will be log n time. We're assured of that. The idea will be all you have to do for work is a rotation, possibly, double or single, and then also before that you'd have to recalculate the height, which would come before the rotation. Recalculate the height and balance, but that's constant time work as well, because to know your own height, you have to figure out the maximum of your subtree heights. Your subtrees would store their heights in the root nodes, and you have direct pointers to those. And likewise, to figure out your own balance, you read the subtree heights. Well, those are stored in your left and right children. So that's quick to do, and then you do a rotation if need be, and then you move upwards to your parent. And so all this is going to be constant time. And then that means that you have total of log n of them. And so log n of these nodes times constant time work at each one is going to be equal then total of log n time worst case for the rebalancing work. And that's what we needed. We talked about that last lecture, that the rebalancing work couldn't take more than log n time. Now we're sure that it won't take any more than log n time, because we're only going to be doing constant amount of work at each node, a rotation, either single or double, plus checking heights and such. So that's part of the where. As you work up from the bottom, any node you find who has a new balance of plus or minus 2. And as far as which rotation to apply, that can be seen by drawing this picture here. We say here, let's say this is some node x. It has a balance of plus or minus 2. I'll put an L here and an R for left and right children. And then you have, when you deal with this, the left child has subtrees. We'll say these are subtrees A and B. The right child has subtrees. We'll say C and D. And so to figure out which rotation we want, we ask two questions. when we have an unbalanced node X. Question 1. Which of X's subtrees is of greater height? So we have this unbalanced node X, and by unbalanced, I of course mean not a legal balance. So 0, +1, or -1 would be okay. When we have an X that has an illegal balance, an unbalanced balance that doesn't qualify as part of the balance definition, and that's +or -2, we first ask which of X's subtrees is of greater height. And if the answer to that is left, then that means we're going to do a right rotation. Because if we have too many nodes on the left, we have to rotate to the right to move some of those nodes to the right. Likewise, if the right subtree had been the one with the greater height, we'd need to move to the left and rotate some nodes to the left to fix that. So we'd have a rotation in that case. So that's question 1. Depending on which of the subtrees has greater height, if there's more nodes on the left side, you have to rotate to the right to fix that. If there's more nodes on the right side, and therefore if there's greater height on the right side, you have to rotate to the left to fix that. Question 2 is, let me actually not do that. Given your answer to 1, which of that subtrees is greater height? Given your answer to question 1, which of that answer's subtrees has greater height? So we're saying if you answered left subtree in part 1, I have to put this back. If you answered left subtree in part 1, which of the subtrees of the left subtree has greater height? If you answered right subtree in part 1, which of the right subtrees has greater height? That's what we're asking here. Which of these 4 sort of grandchildren of X, those subtrees, which of those have greater height? And the answer is, if your answer is an inner subtree, or I should say first, let me do outer first. If it's an outer subtree, or in other words, if it's the left child of the left subtree of X, or the right subtree of the right subtree of X, then that means you do a single rotation. Or in other words, going back to the picture, if the left side has more nodes and A has more nodes than B, then we can do a single rotation on X to fix that. And that was our first example, the single rotation example. The left subtree had more nodes, and then we had inserted into A, which meant A then had more nodes than B, or we had a greater height than B. Generally here, you're going to have, whenever a subtree has more nodes, it'll also, if it has greater height, it also has more nodes. Likewise, if I had a mirror image of that, that would be something like if I had to insert it into D, where the right side has greater height than the left side, and of the right 2 subtrees, C and D, D would have been the one corresponding to A that had stuff inserted into it. And so that's what we mean by outer subtree. On the other hand, if you answer inner, which in other words would be so the left of X was A, and the right of X was D. The right child of the left child of X, and that's subtree B in that last picture, or the left subtree of the right subtree of X, and that's answer C, and the answer here is that we have to do a double rotation. So now we've got all 4 of those pictures covered. If we insert into an inner subtree, the right child of the left child of x or the left child of the right child of x, that's a double rotation. And let me point that out in the back picture here. B is the right child of the left child of x. C is the left child of the right child of x. And they're on the inner ends where the A and D are on the outer ends. Looking at the 4 trees, they could sort of be grandchildren of x. The children of x, those 4 positions are what we're looking at. And that's where A, B, and C and D correspond to. And the idea is if B or C is the one causing the problem, as we've already seen, a single rotation just moves it to the other side. Where a double rotation will basically convert the things being in the outer to things being in the inner. The first half of the double rotation says, let's change it from a situation where B is the problem to a situation where A is the problem. And therefore, the single rotation can fix it. Or alternatively, it says, let's change it from a situation where C is the problem to a situation where D is the problem with step 1. Then step 2 fixes D, just like it would have if we did a single rotation to begin with, and things had been problem with D. If your problem's with A or D, one rotation fixes it, a single rotation. If the problem's with B or C, then you do a first step that's a single rotation to make it a problem with A or D instead, and then your other single rotation will fix the problem. And so those 2 together are a double rotation, and that's what you do with B or C. So that's the which rotation to apply, and with that we're done. The way to do an AVL tree operation, now we can sort of kind of peek through previous slides here. We do your binary search tree operation. We move down to where you insert or remove a node. Once the binary search tree operation has been done, then we kick in the rebalancing work by looking at the parent of the node you inserted or removed. As you start moving upwards, you look at the parent, and then its parent, and then its parent, and then its parent, back along the same path you traversed recursively, back up that path up to the root. And at each node, you readjust the height and balance, and then ask, is this balance now plus or minus 2? If so, that's where to apply the rotation. You then ask the 2 questions I just put up, this question 1 and question 2 on the other slide. Given those 2 answers to those 2 questions, that tells you which rotation to apply. Now you know where, you apply it here. You decide which rotation to apply based on those 2 questions, and then you proceed to then do the rotation, because we've discussed how to do all of them. And so that's the idea here. Binary search tree operation, and then recursively move up and check the nodes along your path one by one in the reverse order. At each node, ask if the balance is plus or minus 2. If it is, then run the 2 questions to decide which rotation you want to do, and then you do that rotation. And that's an AVL tree operation right there. We can talk next time a bit about the philosophy of things, but let me go ahead and write in the summary here of this. Single right, double left, single left, depending on which tree is the problem. We can talk tomorrow about a little bit more about the philosophy of this, or kind of looking at it from a different angle, why I think, what patterns you can expect to see as you do inserts and removals. But basically, that's the summary of an AVL tree operation. For insert or removal, do the binary search tree version. Then as you return from your recursive calls, inspecting that path you just traversed down in the opposite order, at each node, update the height and balance, and then check and say, is this balance plus or minus 2 now? If it is, you use this formula to pick out what rotation to do, and then you do the rotation. And that's your where, which, and how. Where do you apply the rotation? At any balance -2 node you encounter as you traverse back up the tree and adjust balances. Which rotation do you apply? This is the answer to that. This summary right here. Whichever tree is causing the problem, you pick from there. And then how do you do the rotations? Well, we've talked about that already. Kind of the twist the tree idea. And that should be enough to start doing examples. Now, the examples might be very difficult for you at this point. Certainly, I would expect they would be. Adams, in a section video, is going to be kind of covering some more examples and such. And then what we will talk about in the next lecture is a little bit more of the patterns you can expect to see with insert removal, and that might make it easier as well. For now, however, that's basically it. You've learned what you need for AVL trees, what they are, the definition of the AVL tree, and also how to actually fix things, how to do insert and remove. You do the binary search tree operation and then the readjustment work as we've talked about here. So with that, I will close the lecture, and we will talk about kind of the expected patterns tomorrow, and that will then finish off the AVL tree lectures total. But for now, you've got enough to actually do problems, and so I will leave things at that. Take care, and I will see you next time. One other note I want to make sure you're clear on: the next lecture is 19, not 18. I'm numbering the lecture videos the same as the lectures themselves. And as you'll notice once you look in the notes page, it's not there now, but I'm going to fix that next. So you'll notice when you look at the notes page next that lecture 18, which was Wednesday, was Wednesday the 4th, was a time I didn't give any lecture in class. It was a review session for the exam. I had a review session in the evening here too, but we are required by university regulations to give people time off if there's an evening exam. So we have that lecture that we cancel, but I tell the students, I'll be here anyway to answer questions if you want. So there was no class formally on Wednesday, therefore there was no lecture, but since I kind of record Monday, Wednesday, Friday every time in the notes page, I always put a placeholder on the notes and say, there were no notes because there's no lecture today, it was a review session, and that's lecture 18. So therefore, there is no real lecture 18. Rather than start renumbering everything after that, I count that as lecture 18, and the next material is lecture 19. So when you look on the page and see lecture 19 and ask what happened to 18, well, 18 was a review session. There was no material. Don't worry about there being no lecture tape there. There isn't, and there won't be because there was no lecture. That said, now we're done, and I will see you next time. Take care.